Dr. Han?
Yeah, hello, everybody. What should I have to say? I mean, the good morning or the good afternoon?
Both. Good morning and good evening, Dr. Han.
Okay. Yeah. Also, that this might be my first time to see the Dr. Ruth Boumphrey. Very nice to meet you. Yeah.
Good to meet you too. Thank you, Dr. Han.
Yeah. Yeah. Time is now up, and also that. May I start today's web seminar? So then we may now start. I proudly announce to open this interesting webinar on technology demand for safety of future ship. This webinar is co-held by HD KSOE and Lloyd Register Asia. First of all, I would like to give my sincere welcome to all the attendees from all over the world. Wow, so I am Song Han, working for HD KSOE as a research engineer, and I feel obliged to mention Mr. Songgu Park from Lloyd Register Asia gives his precious support to this webinar as well. Of course, the Professor Yong-Han Kim played the very much committed role to organize this webinar behind the scene. Without Mr. Kim and Professor Kim's effort, we might not be able to meet at this nice webinar. Yeah, thank you very much. As already informed through the webinar announcement, we are going to touch a number of the important topics, which include how to evaluate safety issues of the future ships. So what is the future ships? Then you can identify from today's schedule, the future ship include ammonia-fueled ship, liquid hydrogen carriers, and autonomous ships, but not limited to these new types of ship. We can also find new technologies which are being newly highlighted these days, such as onboard carbon capture and storage, and ship dynamic stability, also digital transformation, and I should not skip these items. Last thing, yeah. So I am also very pleased to see most renowned professors, research engineers, and top managers from Japan, Korea, United Kingdom, and the States willingly join this webinar as a presenter and the audience as well. Even though we are gathering at this tricky time, but I believe this time difference will not be any blocking elements to this planned technology exchange effort. If you look at the detailed schedule, we put a coffee break as time buffer, and after that, one video recording will be played from the stage. I think this might be, the place does not wake up yet. So I think now we are ready to invite two renowned guests from HDKSOE and Lloyd Register Foundation for congratulatory speech. We are going to have the Dr. Ruth Boumphrey, the CEO of Lloyd Register Foundation, followed by KSOE CTO, Dr. Hong Chang. Please welcome Dr. Chang first for his speech.
Okay. Yeah. Good morning and good evening. On behalf of HD KSOE, I would like to thank you for inviting me to participate in the webinar, Technology Demand for the Safety Future Ship. I'm very pleased and honored to attend and speak at this important event. Like other industries, the shipbuilding sector is facing huge challenges to meet the demand of future decarbonization. The International Maritime Organization has introduced a stricter regulation with a goal of carbon net zero emission by 2050. Solutions to achieve this goal can be broadly divided into alternative fuels and energy efficiency increase through new technology. For alternative fuel, ammonia and hydrogen are expected to be important, and we are already seeing orders for ammonia-powered ship and ammonia carrier from some clients. In terms of energy efficiency, autonomous operation and digitalization of ships are expected to be the most promising. As I mentioned earlier, ammonia and hydrogen are expected to play a very important role in achieving the shipping industry's decarbonization goal. However, the application of these carbon-free fuels to the shipping industry must take into account their safety for people, assets, and the environment. I believe that assessing the safety of future ships using carbon-free fuels such as ammonia is not just a problem that only one company can solve, but a major issue for the society we live and a challenge that we must solve together. In this regard, I think today's webinar is a very important topic and a meaningful start. I hope this seminar will give you an opportunity to think about how to apply fuel and related technology to the ship of the future. I would like to thank everyone for their hard work in organizing this seminar, especially like to thank all speakers today. And I hope you have a great time. Thank you.
Thank you very much, Dr. Chang.
Thank you.
And may I ask Dr. Boumphrey for your nice speech, please?
Thank you so much. I am Ruth Boumphrey. I'm the Chief Executive of Lloyd's Register Foundation, and I'm hugely honoured and privileged to be here to say a few words at the beginning of this very important webinar. My first thing that I want to do is to celebrate our long relationship with Yong-Won Kim, Professor Yong-Won Kim, who has supported the Foundation's work to engineer a safer world for over a decade. And we've come to you again, Professor Kim, to help us to set forward our future agenda. So we thank you for your leadership and the partnership we have enjoyed with you. Second, I want to thank everyone who is participating in this webinar today across many time zones. It's truly impressive, the people who are staying up late and the people who are getting up early in order to be part of this event today and to share your knowledge and to learn from each other from across the world. Shipping is facing three big threats, but even many more, I know. But if we look at this, some three big threats, there is the threat and the opportunity of new technologies. How will we incorporate and use new technologies for safety? There is the threat and the opportunity in the transition to zero carbon, which is desperately needed in order to keep climate change in manageable portions. And that is a huge technological and industrial and infrastructure challenge, which exists for shipping, but well beyond into the infrastructure for our planet. And the third area is acknowledging that climate change is taking place and that the weather and the way the sea state is changing as well, that we must prepare ourselves for that change in the sea state and the way that the ships and our port systems will have to be built in response to climate change. So with those three big challenges, what we're doing today is a step forward in sharing our vision to cooperate on safety. And we need to cooperate on safety as we design, build, operate, and decommission the ships for today and for the future. Safety is a basic principle and a shared principle for all of us. And there will be no progress in what we need to do without cooperation around safety. So thank you for participating today.
Thank you very much, Dr. Boumphrey, for your nice speech. So I'd like to ask the Professor Yong-An Kim to take care of the coming presentation. Yeah, he's going to take care of the older presentation instead of me. So I'll be standing outside rather than in front of you. Yeah, please.
Okay, Dr. Han, thank you. But we need a congratulatory speech by Mr. Sung-Gu Park. So I will start from here, but please do so.
Okay, thank you, Dr. Han and Professor Kim. First of all, sorry for my background, because last time Professor Yong-An Kim asked me to do the moderator role for this event through this tour, but I tried to change it, but I failed. So first of all, sorry for this one. So next time I will update my background anyway. Okay, thanks again to Professor Yong-An Kim to organize this webinar. As I believe, we have to understand the technology demand for safety assessment of future ships. And we also have to identify the research scope and direction for future ship technology related to the ship safety, which is the main objective of this webinar. Over the past decade, maritime industry have made significant progress in decarbonization. Introduction of EEDI in 2013 and EEXI CII in 2022 have significantly increased the efficiency of both newly delivered and the existing ships since 2013. Recently, IMO amended greenhouse gas strategy, which has now set a revised target to further increase efficiency and move to the industry to net zero emission close to 2050, which has expedited maritime decarbonization. In addition, like the other industry, maritime sectors tend to benefit from digitalization. Commercial ships will increasingly rely on machine learning, AI, and satellite technology to improve shipping safety and efficiency. So today's empirical model processes only about 10% of vessel data, comparing with 90% for AI model, which can generate accurate performance insight. In this way, AI-driven model can optimize decision-making and even address safety issues that may arise due to lack of situation awareness or data. By 2050, there is a possibility that remote-controlled or even fully autonomous small commercial ship could operate near coastal area with absolutely no crew on board. In envisaging this path ahead and rapid change, we have experienced over the past few years, digitalization enables maritime industry to be decarbonized with require new technology deployment to the asset. Therefore, I'm looking forward to technical presentation and constructive discussion about exciting topics ahead. Thank you very much.
Thank you, Mr. Park. You gave a very important points.
Thank you, Professor Kim. Good morning, good evening, everyone. Thank you for the invitation to contribute to the discussion about such an important area for the industry. Today, I'm going to talk about ammonia. And I'm going to go back to some of the fundamentals, because understanding a material and understanding the properties and behaviors of some of the new fuels is very important to understanding or implementing the technology to control them effectively. So just to dive straight in, when we talk about ammonia and when you talk about future fuels, you quite often see in the various reports and documents tables of this type. So they set out a whole number of material and hazardous properties. And it's not easy to see at a glance what these tables of data mean for us. So I just want to spend a bit of time picking out a few features of this table that compares ammonia with a better known and already adopted fuel, that is methane, the main component of LNG. The first thing we see is a set of flammability properties. So when we look at the numbers on the left and we look at the numbers on the right for methane, what we see is essentially that ammonia is less flammable and much harder to ignite. So ammonia is only flammable down to a concentration of 15% by volume, whereas methane is flammable down to a concentration of around 5% by volume. The second thing we see is that the minimum ignition energy, the energy needed to start combustion in a flammable mixture, is much, much higher for ammonia, sort of 680 millijoules compared to 0.3 millijoules for methane, which tells us, as I say, that the ammonia is much more difficult to ignite. The next thing we see on the ammonia side of the table is that unlike methane and other conventional fuels, ammonia is toxic. It's toxic in terms of discomfort and irritation down to levels of about 30 ppm for a 30-minute exposure. At a level of 1600 ppm for a 30-minute exposure, we could be looking at fatalities among the exposed population. An important factor to consider when we think about toxicity effects in relation to flammability effects, when you think about a flammable concentration, so the flammable concentration for methane of 5.3% corresponds to 53,000 ppm. And we are looking at concentrations of concern for ammonia down to 220 ppm or maybe even less. Generally speaking, what this means is that the hazardous effects of ammonia tend to be longer range than the flammability effects of other conventional fuels and LNG. So the effects we need to consider when we're talking about the design of a vessel can be longer range than the flammability effects that we're used to. The final feature of ammonia is that it's soluble in water, which can be a good thing. So in terms of being able to mitigate a spill and the vapor that's produced, a water curtain may help. But we need to be conscious that technologies like water curtains are not 100% effective. So although we may deploy a water curtain, the factors governing its effectiveness, like the droplet size, the water flow rate, where the water curtain is positioned in relation to the release of ammonia, are all important factors governing its effectiveness. A downside to solubility is that when ammonia dissolves, it produces heat, and the heat can drive further vaporization of a liquid pool. So applying water or accidentally having water dripping onto a pool of liquid ammonia can actually increase vaporization. So water needs to be used in mitigation very carefully. We can learn a lot from what we already know about designing ships with fuels like LNG in terms of the engineering practices that we need to apply to design safer ships. But we need to remember that when we do that, ammonia is not the same as LNG. It has other properties, and the toxicity particularly means that the designs that we create will not always be exactly the same as for an LNG fueled ship. And thankfully, class societies like LR and other societies are starting to produce rules and guidelines for the design of such vessels. It's also important that we understand the behavior of the fuel, and particularly the difference between refrigerated ammonia and pressurized ammonia. And of course, semi-refrigerated ammonia sits somewhere in between. So when we have a spill of refrigerated ammonia at its minus 33 centigrade boiling point, what we see, depending of course on the hole size and the pressure, but generally speaking, what we see is an initial release with a low fraction of vapor. So most of the release as it is emitted is actually liquid. As the liquid cools the surface onto which it falls, you can get a pool, a pool of liquid ammonia formed, which then vaporizes to release ammonia into the atmosphere. Now, because the liquid is cold, the cloud that's initially formed is dense. So that dense cloud can stick close to the surface. It can stick close to the surface of like such as the deck of a vessel, although later on it will become less dense and start to lift off from the surface. If we look at a similar condition for a similar scenario for a pressurized release of ammonia, the flashing of the ammonia as the pressure is relieved and the liquid leaks out into the environment produces a very rapid flashing of the liquid, producing a mixture of vapor and droplets. And now it's possible for some of those droplets to rain out onto the surface. But as a general rule, we see less pool formation and subsequent vaporization from the pool in the case of a pressurized release compared to a refrigerated release. And this is quite important. Again, as the liquid flashes, the vapor actually cools down to the boiling point of minus 33 degrees centigrade. So the cloud is initially dense again, even though the material was initially at a higher temperature. Because we have less pool formation, the mass enters the cloud at a higher rate. In other words, the liquid is not held up in the pool in the same way that it is for liquid ammonia. So if we take a given mass release rate for refrigerated ammonia compared to pressurized ammonia, you may well see that the pressurized ammonia has a longer hazard range compared to the liquid ammonia for this reason. So as a general principle, what we see is that the amount of risk mitigation you need to get to an acceptable level is different compared to refrigerated and pressurized systems. In the refrigerated case, you see that you need to apply less technical safety and less risk mitigation to reach an acceptable level of risk than you do with pressurized. When we look at ammonia releases into spaces, so this illustrates in very simple fashion the kind of system we see. We have a ventilation rate, often this is quite high, 30 air changes an hour or something of this magnitude, perhaps even increasing to 45 air changes an hour. What we see is that even with high rates of ventilation, concentrations increase quite rapidly. Now, remember that the concentrations that we're interested in compared to a flammable mixture are very much lower. So we may be looking to avoid concentrations of 220 ppm or even less in this space. But the ventilation does not entirely mitigate that except for the very smallest leaks. So although ventilation provides some mitigation for small toxic leaks and for flammable effects is quite effective at preventing flammable concentrations being reached, it is not always helpful in terms of the toxic effect. And we need to remember this when we're thinking about access and use of these spaces. Of course, we will look to see detection, alarm, and shutdown systems in such spaces. I think it's also important that crew access and time spent in these spaces is controlled and minimized. That intrusive maintenance of ammonia systems is carried out when the system is shut down, isolated, and purged, that the correct PPE is used, and we may well even consider automation of many of the functions inside these spaces to prevent the need for human interaction. Another important point to remember in terms of the behavior of the cloud is how the ammonia behaves once it emerges from the enclosed space and is vented. Structures have wakes like ships. So there are turbulent regions downwind of a structure. And if the release of ammonia is too close to the top of the structure, it can get caught into this wake, even if the release is quite low density, and stay close to the deck for perhaps, depending on the concentrations and the size of the release in the space, perhaps for some tens of meters. So it's important to think about where you position the vents in relation to the areas that crew are expected to access. And we're now seeing this emerge as a requirement in some of the rules and guidelines that people are producing. An issue that doesn't really come up very much when we think about LNG and other fuels is the number of leak sources that we have in any one space. And again, this is really driven by the fact that the concentrations that are of interest to us are quite a lot lower than they are, say, for the flammable concentrations for LNG. So if you consider a crew member who has to enter a space to carry out a visual inspection, maybe only for a few minutes every day, the point is that once they enter the space, they are exposed to all of the potential leak sources in that space, even the ones that they are not inspecting. And it is possible to achieve a risk reduction by dividing our spaces so that the amount of equipment in each space is less. And of course, we need to think about some of the other practical aspects of doing this. But in the work we've done on the risk analysis of ammonia vessels, when this is done properly, we can see a reduction in the risk to these personnel. So just to conclude, ammonia is flammable, but its toxicity is a much bigger concern. Refrigerated in terms of risk and the amount of mitigation that you need is generally better than pressurized. Ventilation of its spaces is effective in preventing flammable concentrations being released, but it's much less effective for mitigating toxic effects. Exhausts close to the roof of a structure can result in the air and ammonia mixture getting pulled into the wake of the structure and down to deck level. And a person entering a space is exposed to all of the leak sources in that space at once, and it may be beneficial to consider using 2 or 3 spaces instead. That concludes my presentation, and thank you for your attention.
Thank you, Andy. It's great, wonderful. You have a very strong points, and it's persuasive. And we have only 15 minutes, but we can take 1 or 2 questions if there is any from the audience. So if there's any question now, you can ask, unmute yourself and ask if you have. Okay, don't be shy. Otherwise, because of time, shortage of time, we have to close this presentation. Let's give a big hands to Andy. Thank you so much.
Thank you. So my name is Song Han. Today, I'd like to have just some introduction of our project, which belongs to Horizon Europe. Our project's name is the LH2 Craft. So in this presentation, I'd like to focus more likely the membrane type, cargo containment system design issue in liquid hydrogen carriers. Please give me the, yeah, okay, fine. Yeah, let me give you some brief details about the project LH2 Craft. This is one of the Horizon Europe project, and this project intends to develop safe and efficient marine transportation of liquid hydrogen. So the consortium of the LH2 Craft project is composed of 12 institutes in total, covering industry, university, and research institute, and classification society. All are from Europe mainland, except our company, HD KSOE. So we are targeting to develop the 160K LH2 carriers. Also that our company's role is to develop the LH2 cargo containment system using membrane type. So to develop this membrane type cargo containment system, we are supposed to make sure the materials are comparable with the liquid hydrogen temperature, which is minus 253, which is quite low. And also, we have to carry out a number of related safety studies to make sure nothing terrible happened. Yeah. So I mean, this is the product. Our product actually the target a great novel sea transportation solution to LH2 based LH2-based industry as one of the sincere measures to achieve the carbon neutral society. We are committed to validate our solution using actual LH2 tank with a viable cargo containment system for liquid hydrogen. To achieve this goal, all required technology disciplines will be put together, utilizing Korea and Europe the technologies background. So you can see that from this slide, so the one side, from bottom, from the very basic technology, but at the end of the project, we are going to prove the technology development using actual, let's say, mobile model. Yeah. Sorry, it doesn't go. Yeah. So our company's role in this project is clear. We are supposed to develop the membrane type cargo containment system, but to do so, we need a certain module ship. So currently, we are targeting 160K cubic LH2 carriers, which is quite similar to the similar size to the 174K LNG carriers. So I think in our development, we put forward 2 important requirements as shown in this slide. So one is actually this cargo containment system should be able to hold cryogenic liquid hydrogen cargo. So to do so, the system should have the excellent insulation performance to guarantee a kind of viable boiler-proof gas. And also that at the same time, the system itself show its recovering function against any failures such as the leak of cargo. So, and the other requirement is the design, the CCS should have the robust structures. So I put down a number of the characteristics to have the robust structures. So first, I mean, mainly those are from the cryogenic liquid hydrogen properties. So, I mean, let's say due to the very low temperatures, then we can expect a large contraction from the containment system. Also, this containment system should have sufficient strength against internal pressure or external loading components as well. Also, that all the components should have the liquid hydrogen compatibility. So simply, there is no chemical reaction with the contact of LH2, and also that no deterioration in mechanical properties, even after LH2 direct contact. Especially the hydrogen is quite cold, so we can simply expect there are two types of embrittlement phenomenon may take place. One is the hydrogen diffusion. So if but inside the material, the hydrogen diffuse, then the material's mechanical property will be dramatically deteriorated. Also, at very low temperatures, then we can expect the material mechanical property becomes quite brittle. So we should be able to define that there is no cryogenic deterioration, such as the brittleness. Also, that currently we need to make sure there is no condensation inside the containment system space. Unfortunately, helium can only exist as a vapor at these low temperatures. Yeah. So I mean, so to be able to overcome these difficulties, we need a kind of the systematic approach. So from this slide, I would like to touch some the basic design principle necessary to complete this challenging mission. So at the moment, we do not have the concrete regulation yet. The only available reference is IMO CCC9 interim recommendation for Type C containment system. The thing is that we are still have difficulties to apply the design, the membrane type containment system for LH2 carriers. So we are supposed to utilize we are supposed to utilize some of for load and resistance factor design should be adapted in this case, but there are some basic things we can utilize from the LNG CCS application. So some of the basic things we may we may borrow the basic safety factors from the LNG application, but there are still other items which still remains as challenging. In that case, we need to resort to first principle, considering the LH2 specific issues. So in this slide, you can see there are demands and capacity. Those are the stochastic manners, and we need to find the sufficient safety margin to have a nice design. At the end of the day, we can finally make sure our design has sufficient safety margin. Yeah. Yeah. So the this reliability concept can be applied in this way. So we define demands and capacity for every design variables. So as the loading components, then the let's say the loading components actually load or apply CCS, then there can be a number of important load components, such as hull girder bending or quasi-static internal pressure, external pressure. But thankfully, those are rather easy to deal with. So we may simply utilize the LNG's experience. So we don't see any significant challenge from this load component. But when it comes to solution impact, then the liquid hydrogen has its own specific characteristic compared to LNG or the other material. So the liquid hydrogen has very low density. Also, it is very easy to transform from the liquid to air, and also that we see that this hydrogen has a kind of large air to liquid density ratio compared to the LNG or the water. So also when it comes to the capacity wise, then we see that the mechanical property and the thermal properties, but unfortunately, all those are affected by the cryogenic temperatures. So as I already mentioned, when it comes to the ultimate limit state or fatigue limit state, we need to make sure there is no cryogenic embrittlement. Also, we need to make sure there is no hydrogen embrittlement. Those are one of the most challenging items we have to overcome. And to be able to evaluate the capacity is bigger than demand sufficiently, we need to make sure the basic thermal capacity property of the component. But unfortunately, some of them are quite difficult to measure because of the let's say to realize minus 253 degree, then we have to utilize liquid helium because we cannot use liquid hydrogen because this is very much flammable. So unfortunately, the liquid helium is quite expensive and it can only make a cold within a very confined areas. So when it comes to large specimen, so then we got a quite tricky situation to evaluate those properties. These are the things that we are now taking care of, and also we try to find a certain way where we can be more comfortable with our decision. And the last item, but not least, this is I have the final issues about the sourcing. So as I already mentioned, the liquid hydrogen has quite interesting features in terms of the density or air to liquid density ratio or the latent heat. From this table, you can see that there is a kind of figures, water and LNG and LH2. Then the LH2 has quite low density, and also that it has very low value in air to liquid density ratio, which is 0.2. Sorry, but that's very high density ratio compared to LNG and water. This means that if we carry out the slashing test using water and air, then we may have some very much the conservative assessment for the slashing impact. Of course, at the moment I cannot say that there is conservative or optimistic, but from our experience of the LNG, then we can easily say that if this value becomes bigger, then the slashing pressure prediction evaluation becomes also becomes very wrong if we do the solution test with water and air. So that's why the for LNG cases, recently water and heavy gases are used to recover this air to liquid density ratio. But there is another item, latent heat of the vaporization. So water boils air, but its latent heat is quite high, so it doesn't easily boil. But if you see the LNG and LH2, then the value is very low compared to the water. Even the LH2 value is quite low compared to LNG. As of today, it's not easy to whether we can say this gives us conservative or optimistic. So considering all these factors, I cannot say what kind of the combination, let's say the water and air or water and heavy gases or something else. So this issue should be first resolved before we make we are comfortable with our design. As of today, simply we may utilize the density difference, but this is the current very unknown areas we need to overcome. Yeah. So actually, this is all. There also that unfortunately from the Horizon Europe, this kind of the slushing issues will not be covered in detail. So we expect some of the nice feedback from let's say, the Seoul National University work. Yeah, thank you very much. This is all my presentation.
Thank you, Dr. Han.
Hey, hello, everyone. My name is Young-Sum Lim, and today's my topic is the issues of the onboard carbon capture and storage. Let me introduce myself in a short time. I have been working in here Department of the Naval Architecture and Ocean Engineering around 10 years. But my background is chemical engineering, especially the process systems engineering. So mainly I have been researching about various kinds of the process system, especially the gas treatment system, such as the carbon dioxide or the LNG BOG liquefaction, the regasification, or the hydrogen handling, something like that. This is the contents for today. So I'll talk about the necessity of the onboard carbon capture and introduce to you some major issues of the onboard carbon capture and storage. Because of the lack of time, I cannot introduce all of the issues, but so I only bring some interesting things for you. So let's start. This is a controversial question. So onboard carbon capture and storage, is it really necessary? This is quite hard question to answer because we all know there is no detailed regulation or law yet. So we cannot say about a specific answer to this question. But my opinion is probably yes. As a temporary solution for specific ships, we may need some onboard carbon capture and storage. Let me explain the reason. So this is an example. You already know to use the hydrogen for economic production of the hydrogen, we need to produce the blue hydrogen. And for the production of the blue hydrogen, the carbon capture and utilization and storage is required now. Because to produce the green hydrogen based on the renewable energy, too much money is required now. So instead of when we combine the carbon capture technology with the gray hydrogen production system, we can produce hydrogen at much lower price. So this is a feasible solution. And if we want to use the carbon capture, utilization, and storage, actually some transport of the carbon dioxide is required. This figure is the one example, the Northern Light project, to capture the carbon dioxide from the Oslo or Breivik and transport it to some injection platform here. And to transport the carbon dioxide, liquefied CO2 carrier is now considered. Then the question is, if we want to produce the blue hydrogen, and then if the CO2 carrier used for the production of the blue hydrogen emits any greenhouse gases, then what happens? In MEPC 80s, we already know they announced all the greenhouse gas emissions will be evaluated based on the well-to-wake emissions. So from the production to the use of the fuel, all kinds of the process could be included in the evaluation of the greenhouse gas emissions. So from the view of the LCA, the greenhouse gas emissions from a carbon dioxide carrier could increase the well-to-wake greenhouse gas emissions of the hydrogen fuel and even any synthetic fuels produced from that hydrogen. So in this case, the onboard carbon capture could be required. So this is the reason I think this can be a temporary solution for specific ships. So let's just see some technical issues of the onboard carbon capture. The first one is the concentration. Carbon capture technology is quite a mature technology, so there are so many researches about that, and they have been reporting when the concentration of the carbon dioxide in the exhaust gas, then required energy is decreased. Typically, the carbon capture system have been applied to the coal-fired power plant, and in this case, the concentration of the carbon dioxide is around 15%. But as we know, unfortunately, for a ship engine such as DFD or gas injection engine, the carbon dioxide concentration is only around 3%. So it means we need to input much more energy comparing to the onshore power plant. So to design our onboard carbon capture system, we should consider this low carbon dioxide concentration issue. If we want to decrease the energy required for the capture, we can combine the heat recovery technology for the carbon capture system. The most commonly used carbon capture system is using the amine solution. So using the absorption, we can capture the carbon dioxide. In this system, the most energy required for the carbon capture is the heat for the reboiler here. So if we can use the waste heat from the exhaust gas, then we can decrease the required energy for the carbon capture. But the problem is, for a ship, the waste heat is quite limited. So how much of the heat we can use for the carbon capture, it depends on the situation. So for the onboard carbon capture, we should consider this waste heat recovery system also. The worst thing is the process conditions on a ship always changing. This is one ongoing project I am doing with the SINTEF Norway, and this is one example of the profile of the container ship operated by the Klaveness. And as we know, it has various kinds of the engine load of the profile. When engine load changes, everything is changed. The temperature of the exhaust gas changes. The flow rate of the exhaust gas also changes. Even the concentration of the carbon dioxide in the exhaust gas also changes. So it means if we want to design the onboard carbon capture system, we should consider all these varying conditions of the process system. If we do not consider it, then we cannot make the optimal process design. Much issues with the impurities. Here I only talk about the water. As we know, water in the exhaust gas may cause icing or the hydrate formation during the liquefaction of the carbon dioxide because we required -50 or the 40 Celsius of the temperature to liquefy the carbon dioxide. So it means if we want to liquefy the carbon dioxide, dehydration is inevitable. Then how much dehydration is required for the exhaust gas of the ship? That's the question. This is the another ongoing research with my colleague of the Professor Seo, and you can see with the changing water content, the hydrate formation zone is moved to like this one. So it means to decide the proper specification, we need some thermodynamic simulation validated by experiment. This is one of the important issue in the carbon dioxide handling. Okay, then let's move to the onboard carbon dioxide storage. In this stage, the storage means not the sequestration storage into the geological formation, the temporary stage on a ship. The first one is the BOG. As we know, when we transport the low temperature liquid, then the boil of gas is generated. Liquefied carbon dioxide also has low temperature, so it evaporates during the transport and become a BOG, and it may cause self-pressurization in the tank. This is quite important issue because the increasing pressure in the tank may cause some safety issues. And this self-pressurization is quite complex phenomenon. The left graph is showing you, this is the research performed by NASA. So it is giving you the information about the self-pressurization of the liquefied hydrogen. And it gives us this red dot is the liquid level of the 50%, and this purple dot means the liquid level of the 90%. So it is giving us the different liquid level gives the different rate of the self-pressurization. So when level change, the speed of the self-pressurization is also changed. And if we assume the equilibrium stage on a tank, then the estimated pressurizing speed is quite slow comparing to the actual situation. So it means we need a quite good model to estimate this situation. The right figure, this is the research I did with the Samsung Heavy Industry, and this is giving you the self-pressurization of the LNG storage tank. And also it gives changing the liquid level gives us the different rate of the self-pressurization. And if we assume the equilibrium condition in the tank, that it may guess very wrong estimation here. So we need to have some exact model to estimate this pressurization speed. Also the impurities. Pure carbon dioxide relatively have lower problems, but unfortunately, if we transport the carbon dioxide captured from onshore sources, may have some light impurities, such as the nitrogen or hydrogen or carbon monoxide, something like that. And these light impurities may exist in much larger portion in the vapor, even we have a very small portion in each liquid. For an example, if we have only 0.5% of nitrogen in liquid phase, when it evaporates in the vapor phase, the concentration of nitrogen can reach around 10% or even more. And these light components may accelerate the pressure rising of the CO2 storage tank. So when there is an impurity in the carbon dioxide tank, we should be careful because the pressure rising speed can be faster than the pure carbon dioxide. So it means we must have much more exact model to estimate the pressure rising speed of the carbon dioxide and considering the impurities. One another issue is the reliquefaction. as we are doing for our LNG carriers, we can apply the boil off gas reliquefaction system. So we can apply this application to an LCO2 carrier also. But the problem is when right impurities exist in our liquefied carbon dioxide storage tank, because we do not consume carbon dioxide, this right gas is recycled this reliquefaction system always. It never be perished. So this recycled right impurities gives some penalty to our reliquefaction system. So the required energy consumption of our reliquefaction system increased when there is some impurities in our carbon dioxide contents. This is one example I am doing with my students. So if we have more nitrogen contents in the carbon dioxide VOC, the required energy consumption for the reliquefaction system will increase almost linearly. So this is one of the important issues also. So conclusion. So we do not know the future. So I cannot say it will be required or not yet, but if there is a possibility, I think we need to prepare. So the onboard carbon capture and storage system, we should consider it. And there are various kinds of technical issues. I only introduced some of them, but there are so many other kinds of issues we have. But as a researcher, I think it is not only the bad things, because it means we can do a lot of things for the future research. So I hope we can do that kind of research in future together. Thank you, everyone. I finish my presentation here.
Okay, thank you, Professor Lim. So if there's any question, we can take one very short question, if there is any. Okay, otherwise we have to close this one. Okay, thank you again.
Today, my topic is the safety of future ships, including the autonomous ships and those green ships also. So the first, let me briefly introduce about my university and department. So I work for NTNU, the Norwegian University of Science and Technology, and my campus is located in Trondheim here. And we have about 43,000 students and 8,000 employees. So NTNU is the largest university in Norway. And I work for the Department of Mechanical and Industrial Engineering. In our department, we have several research groups like this. And I belong to the group called RAMS. It's the reliability, availability, maintenance, and safety. And in our group, we conduct the various kind of safety-related research on the offshore, the wind, and hydrogen, and transportations, and so on. And I did my PhD from here at NTNU about the topic of maritime safety. And before I came to Norway, I worked for the Samsung Heavy Industries about 7 years. And I did my master's and bachelor's degree in South Korea on the naval architecture and ocean engineering. And I am involved, or I was involved for several research projects. And some of the relevant projects with today's topics are some autonomous ship projects in Norway and in South Korea, and also some green energy solution project also in Norway and in South Korea. And today I wanted to talk to you about the future ship safety and two main issues. One is the hazard analysis, and another one is the quantitative risk analysis. So let's start from the future ships and the risk assessment. As we all know, we have two main research topics in the maritime industry now. The one is the emission reduction, and the other one is autonomous operation or digitalization of the vessels. So we have many projects like ammonia-powered vessels or hydrogen-fueled ships or battery-powered ships, and also many projects for the autonomous ships or utilizing digital technology for the ships. And as you know, in both cases, we don't have any descriptive requirement for those new future vessels. And most of those guidelines or some standard, they require to conduct some risk assessment for them. And IMO, they provide some guidelines how we can conduct those risk assessment, right? And normally in maritime industries, we use some traditional, very well-known and widely used risk analysis method for the ships. So those methods are very famous and widely used, but there are some challenges and limitations there. So the objective of today is to address some challenges of this traditional risk assessment method and suggest some possible solutions for them. So we can start from the hazard identification first. So for this, we use some method called HACID or FMECA or FMEA. So this HACID and FMEA looks like this. So, we do some brainstorming, and based on this brainstorming, we identify some possible hazard or hazardous event and causes and consequences and so on. So this is very widely used method in the maritime industry, but there are some challenges and limitations on this method because this method is based on the brainstorm. So the quality of the result is highly dependent on who analyzed the system, right? And the second, especially for the FMEA, we analyze the component failure, the single component failure. But in the real world, we may have multiple failures at the same time, or we can have one failure that can affect some various kind of problems, or even we may have an accident without any component failure because of this complex configuration of the system. So there are many arguments that using those traditional methods for future ships may not be enough to analyze or to identify every kind of possible hazardous scenarios. So maybe we can adopt some new and advanced hazard analysis method. And one of them can be a method called STPA. STPA is the System Theoretic Process Analysis. And this is a hazard analysis method based on STAMP theory. And this theory, the main focus is that the accidents are not caused by the failures. But most of those modern accidents, they are caused by very complex control actions. So the main objective of this method is to analyze unsafe control actions, meaning some control actions that can lead to an accident, and to identify loss scenarios. Loss scenarios mean the reason why we have those unsafe control actions. And this method is widely used in various sectors and domains, especially for aviations or aerospace or nuclear power plants, but not in maritime industry yet. Then you may ask why we need this new method, because even we have some traditional method like HACID or FMEA. But the reason why we needed this new method is because this method was recently developed for modern complex systems. The FMEA was developed in 1940s, and HACID and PHA, one of the HACID method, was developed in 1960s. And the technology has been developed a lot like this. And it is the same for the ships. The photo in the left-hand side is the engine control room in a warship in the Second World War. And this one is the engine control room in a modern cruise vessels. And this is why the FMEA focuses on the component failure, because all those control was conducted by a physical system. But now we have much more critical issues other than the component failures in these complex systems. And STPA was developed to analyze this kind of modern, complex, and software-intensive systems. And this method is based on the systems theory, so it adopts a kind of top-down approach. So we can use this method from the very beginning of the project or design, unlike FMEA, because in FMEA, we analyze the component. So we need certain amount of the design. So we cannot use FMEA from the very beginning of the project, but we can use it in the beginning phase of the project. And the STPA can also provide wider scope than the other method, like including component failures or human errors, and also software errors or very dangerous interactions and so on. And there are many studies that support that STPA could identify more problems than the other method. So this method is being adopted as an industry standard, especially for the aviation and the automotive industry, and for the self-driving car, for instance. And I have applied this method to various applications like subsea or autonomous ships or battery ferries or automated port operations. And this is an example. So unlike HACID or FMECA, we don't rely on the brainstorm, but we analyze the system first. So we identify what kind of controllers we have in our system, and what kind of control commands they have, and what kind of feedback they will receive. And we examine those control commands one by one, so we can more systematically identify those hazards from the system. And the advantage of this method is quite opposite to the limitations of a traditional method, because this method provides very well-structured and detailed procedures. So the quality of the result is not so much dependent on who analyzed the system. And in addition, this method can analyze not only the single component failures, but also the multiple failures or the complex interactions of the system without any failure. So this can be one possible candidate method we can use for the future ship safety. And the next point is about the quantitative risk analysis. So for this, we normally use a method called the fault tree analysis here and the event tree analysis. And we use some historical failure data. Then we can calculate some numbers. It is an average risk per year or risk per month or something like that. And this average risk is, of course, constant against time because it is an average. And we design the system that our average risk is below than the acceptable risk. But the risk in the real world is not average, right? The risk varies a lot depending on the operating conditions. For instance, at the port or in a heavy weather or at the canal, we may have a higher risk than the vessel in the calm and open sea. And sometimes those real-time risks can exceed the acceptable levels. So it's very important to analyze not only the average, but also those real-time risks of the vessel. So in the average risk analysis, we use the system configuration and some historical failure data, then we calculate average risk. But in the real-time risk, we use, in addition to those, we use some real-time sensor data from the system, like temperature or vibrations, and the weather condition, and the nearby vessels, location and speed and so on, and some maintenance law, and even the human factors. We consider all those factors and we calculate the risk at this moment. So the real-time risk is not a single value, but this is kind of a continuously changing number. So we normally express this real-time risk using something called risk barometer like this. And I'm currently working for this real-time risk analysis for CAS project in South Korea. So we use both the fuzzy logic and the Bayesian network, so we can express the level of risk in our vessel at a specific moment. So to summarize, we will have many new technologies for decarbonization and autonomous operation of the vessels. And always, when we have new technologies, then we have always new risks. So we need some risk assessment for those new technologies. But some traditional method may have some challenges. So STPA or real-time risk or other new approach can be a solution to analyze the safety of the future ships. So lastly, I wanted to say that when I presented this to the companies or industries, they normally ask me whether it is required by regulations. Is STPA or real-time risk, is it required by the regulations? Then the answer is not yet. Then they are not interested anymore for this. But I wanted to say that we will have a totally different hazard in the future because of this autonomous operation of the vessels. And we will have much more critical and severe consequence in an accident because we will use ammonia or hydrogen for the fuel of the vessels. So we also need, I think, some new safety approach that can ensure the safer ocean because we don't use FMEA for self-driving car. And we don't rely on the average risk only in the process industry that handles hydrogens or ammonia or other dangerous chemicals. So even they are not required by the regulations, but for a safer world and safer ocean, I think we also needed to adopt some new and advanced safety analysis method. So thank you for your attention. Thank you.
Thank you. Thank you, Professor Kim.
Okay, so thank you very much for introduction. Hi, I am Suguru Fukutomi of Ship Partners. And it's an honor for us to make presentation here. And especially Professor Kim, thank you very much for giving us this great opportunity. So Ship Partner is a Japanese company based in Tokyo. We are doing several businesses. One is exclusive agency service in Japan for Helicon Group and Centurion. Helicon is a British shipping owner owning around 50 ships. And Centurion Bulk is a Singaporean dry bulk operator handling around 70 ships. So we have equity and strategic partnership with them. And we are working very closely with them. And then second one is ship owning and leasing and financing by using our own digital platform. And we as owner have ordered 2 ships, 2 new buildings in the last year. And the third one is a technical advisory service for Samsung Heavy Industry to develop their smart ship and autonomous navigation system. And then fourth one is digital web services for ship valuation and ship finance arrangement and charter party documentation. And then we are doing real estate business in Tokyo, but it is not shipping business. But anyway, we as group, we are very keen to digital transformation of shipping. For example, Helicon Group has already installed the latest satellite system, Starlink, into all of their own ships. So now 50 ships have Starlink system. So we are very happy to use these ships for testing your new technologies if it is developed. And then Centurion Bulk also can advise their feedback as a operator's point of view. So it is very exciting for us to hear new ideas, and we'd like to support good ideas as much as possible. So Jo-hyun Kim, please explain your thoughts.
Good evening to Asia and good afternoon to Europe. And I'm Jo-hyun Kim. And what I'm going to explain today is what we need to solve and the future we imagine as an owner and operator. let me start with our viewpoint as owner and operator. Our role is to operate and maintain the ships. Thus, we are supposed to be responsible for maintaining the safety and performance of ships. If owners orders a new building to shipyard, the shipyard is starting to design. In the past, the ship was designed with the overall stiffeners or overall structures, but the many numerical analytic tools such as the hydrodynamic calculation and the FM analysis tools greatly contributed to the optimal design. And if the ship is constructed, we operate the ships in water. And past and currently, we operate the ships based on the experience, and the maintenance is carried out on time-based inspection and maintenance. And it means that the ship is partially managed. As you know, the ship owners has the obligation to the time-based dry docking and inspection and such as. So it means that the ship is at least partially managed. However, we want to manage and operate the ship in more high efficiency. For example, we carry out the efficient operation with the monitoring and then maintenance with the condition-based, and then we can completely manage the vessel. But it requires lots of the human tasks, so we need a digital solution in this stage. So we are heading for the sustainable high-level operation and maintenance. It is essential to active this high-level sustainable operation and maintenance. The digitalization of the vessel is required. If the ship is digitalized in fully, and then the digitalization gives us the transparency into the ships, and digital solution and assistance service can give us the more insight to increase the high efficiency and performance and increase safety with the minimized uncertainty. So it leads to minimize the inspection and maintenance. Let me show more detail regarding the transparency. The transparency means that the monitor vessel's status in clear. Currently, it's simply it is easy to see the navigation status and engine and equipment status and cargo and carbon footprint is very easy to see. However, the owner and operator want to know changes in performance of hull and engine due to the hull fouling and causes of the excessive fuel consumption due to the wave or wind, and causes and responsibilities of the accident. We may need some camera system or sensing system to explore the causes and responsibility. And we want to know the remaining life of all parts of the structures. And then we want to increase the efficiency and the safety of the vessels. For this problem, we may need some solution to the efficient and safe voyage, and then effective dry docking and maintenance guide, or effective inspection or maintenance, the timing or method, and it leads to minimize downtime and manage the failures. So we think for the high-level digitalization can be carried out by the digital twin. We adopted this picture left side from the Nabuto. Nabuto has also very good philosophy of for the digitalization of the ships. Then we can consider the digital twin into two parts. One is the structural digital twin. It includes the monitoring of hull stress on entire parts, not only on the strain gauge installed, and it also provide the prediction of the fatigue rate and updated by the physical visual inspection and maintenance, and also provide the allowable loading condition with the route. And the another part is that maybe not official, but hydrodynamic digital twin, it should provide the analysis of the environmental conditions and prediction of the extreme values and prediction of the hydrodynamic response and added resistance and speed powers. So this is very familiar with the researchers in design stage, because we do many these tasks for the optimal design of the ships, but we also need these techniques to the optimal operation. So this, we can call it the maybe hydrodynamic digital twin, but we need both of the digital twin technologies. The why digital twin, we'll explain that the digital twin is simply defined as the digital representation of a vessel which is updated in real time, just that. Thus, we have added two requirements, is that full integration into a monolithic architecture, because the vessel is partially digitalized by the sensors. So it is not, we think it is not powerful. And the other requirement is that two-way synchronization. It means that digital twin can control the physical vessel, and then the digital twin can receive the response and data. By these two requirements, we can apply the many digital solutions seamlessly to the real ship. So this is the reason why the digital twin is important for the development of the digital techniques into the real ship operation. Let's see the figures on the bottom of the slide. If the supervisor, could be the human, or will be replaced by artificial intelligence in the future, and the supervisor only interact with the digital twin, and we can command something to optimal action, and then digital twin will control and physical vessel will respond to the digital twin, and we can get the feedback from the digital twin. This is very easy to optimize the ship operation and maintenance. And this is the future of the structural management we imagine. So let's see the left side of this figure. Inside of the structural digital twin, the vessel is, if the vessel is monitored by stress on the entire hull structures, and then some algorithm will calculate the evaluation of the structural safety, and then structural digital twin will provide the locations vulnerable to the corrosion and cracks, and then the robot can visual inspection and measurement, UV measurement of the thickness, and then report to the evaluation of the structural safety. It will provide the checklist to be repaired to supervisor. And the only thing supervisor should do is that manage the RNG and manage the maintenance only. And then the ship will be repaired and then updated the structural safety, and we can get the report, and we'll submit this report to the flag or port state control and classification. This is what we imagine as the future of the structural management. This is our conclusion. It means that the next digital revolution is coming. However, we don't know when, but it is clear that the next digital revolution will come in a form of the fusion of digital solution and AI technology. But it will be brought by the many efforts by all of members of the ship industries. For example, shipyard, manufacturer, academic, research institute, classifications, government, and owner-operator. All of us should do our effort to lead the next digital revolution. Thank you for your attention.
Okay, thank you. Thank you so much. Well, I'm not familiar. Actually, I'm normally use the Zoom, but my students arrange most of things. So doing myself is a little bit hard for me. But thank you. I appreciate for your wonderful presentation. And I know it's a late time like Seoul in Tokyo. But thank you for your participation. I would like to introduce our recent works. Actually, we spent a few years already. This is a very, how can I say, ambitious word. Prophetic is future forecasting. Prophetic, a real-time digital twin for ship operation in actual seaways. And currently, the digital twin is popular, as already Dr. Kim mentioned in the earlier. Everybody's talking about digital twin, but currently the ship operation is based on the vision and marine radar, and the main purpose is to detect the objects nearby. If we go further, then we can define the wave conditions normally done by using the statistical characteristics like a significant wave height or mean period or wave heading. So that's a reality. To be a real digital twin, we need to actually move on, and we need a much advanced technology. Currently, the concept of technology is widely under development, but my concern is rather than real time, it's based on the current technology integration. Okay, so it's okay. In some systems, it's okay. We can define the computer domain to mimic the physics, but sometimes if we can do in real time, that will be very useful. For instance, if you can predict the ship motion and waves and any risk in the actual seaways, that will be wonderful in the real time. Okay, so if you see this future, near future, that's what we call it prophetic system. If we can do, ship operator can operate the ship by using such kind of data and information and simulating the scenarios in advance, see the future. And then to do that, we need some elements. So we need to predict the ocean waves. That's the most difficult part. We are not talking about significant wave height and mean period and wave heading only. We are talking about the real evolution of the free surface profiles. So we have to reconstruct ocean wave profile and also to predict the ocean profile. And also we need to predict ship performance and safety in waves, like operation efficiency, seakeeping, maneuverability, and dynamic stability, structural safety, and collision avoidance, etc. My understanding is we need this kind of things based on the physics. It means we need to combine the physics and digital techniques. Only digital techniques has a definitely limitation. But again, this should be done in real time with a reasonable cost. The basic concept is like that. If you see the autonomous function of nowadays, the car is based on the only vision, LiDAR and the visual sensors, okay? And navigation system is only based on the current traffic situation. Just get the information of current situation and try to find the optimum route. If we can predict the future, what will happen? For instance, if you get the target in activate navigator, and if navigator can say, okay, 2 minutes later, you will face an ambulance in front of you passing with high speed. Why don't you speed up, or why don't you slow down to avoid? The other case is say, oh, we have a school time, closing time 10 minutes later in such a location. Why don't you speed up, or why don't you detour to avoid some risk? Such kind of things. If we can make it, okay, what will happen in the ocean? Basically the same. We can avoid excessive roll. You can avoid parametric roll. You can predict the efficiency. We can find the other way to get there. So many things will be possible. And recently we developed some element which are essential for this kind of system. The most difficult part from the ocean waves, because technically it's difficult to predict the ocean waves. Again, it's a full profile, not 3-hour significant wave height. And if it is possible, we can get the responses like a seakeeping or structural responses or maneuverability. And also we can predict the efficiency in the wind and current and waves, and we can predict the ship operation propulsion efficiency, and we can identify the risk, and we can avoid such kind of risk. Recently, we worked with MIT to develop the wave module. Currently, the X-band radar is being used to detect the wave statistics. It means, again, the significant wave height and mean period. But if if we use the X-band radar, normally the image, it comes through the image, and images are very spiky signals. So there are very thorough mathematical formulations and systematic approaches how to reconstruct the waves. This is a most difficult part again. If we have such kind of reconstruction, we can forecast the wave conditions in near future, and based on that, we can get the responses of ships in different characteristics. This is one example recently we developed. I would like to show two examples. One is the EODO data that is fixed on the bottom, so it's a stationary. The other one is from the ship. So they use the X-band wave radar, and they analyze the wave, and we are comparing the significant wave height. Again, we are not doing the only significant wave height. We can define the free surface evolution, but we don't have such kind of exact data, so we just compare the significant wave height. If you see the fixed case, bottom fixed case, okay, the correspondence with the existing X-band wave radar is quite acceptable. In the case of ship, we found that there are some differences with the buoy data. We checked the buoy data nearby the ship operation area, and we found a very big difference. And according to our analysis, we found that our data is pretty much close to the buoy data. It means we can overcome some technical difficulties that we have in existing systems. Anyhow, this is example. So another example is if we can predict such kind of wave in 10 minutes or 20 minutes or 30 minutes, we can predict the ship motion like heave and pitch and whatever, 6-degree freedom. I didn't include it here, but we can change the trajectories. We can find the risk. And this can be done in the sequential way. What I mean is we measure the X-band radar for 1 minute or 2 minutes. you can predict like 10 or 30 minutes, and we can continue. Then theoretically, this we can do all the time. Okay, that's actually a basic idea. So we made a pilot platform for Daewoo Shipbuilding and Marine Engineering. This was done 1.5 years ago. We delivered the code, the name of twin ship, and it includes the reconstruction of the wave, and also prediction of the wave, and prediction of the motion, and prediction of risk. So in the case of a head sea, we are facing the wave. So prediction time is like, it depends on the expanded radar range, but with a normal range, you can predict like 10 minutes or 15 minutes. But following sea, we have a much longer, more than 30 minutes interval. So we can do this kind of things, and we can define the optimum course to minimize the risk and something like that. So if there is a pilot platform, it's working in all real time. But there are some future issues, and these future issues should be overcome to utilize the more efficient way. That validation, okay, we are lack of validation because there is no system like this. So we have to identify the accuracy, and we have to check the validation, and then the other one issue is wave radar. I have a very doubt that current wave radar doesn't have a good accuracy to measure the wave profile. The other one is the extension. The extension is that actually many extensions are possible. For instance, energy efficiency, whole ship monitoring. We can just plug in the system. Okay, we can integrate quite easily. And prediction of the severe. As long as we have a motion responses, then we can predict slamming occurrence or green water occurrence. And also structure is what we are doing. Even now, we are working with the other organizations funded by Korean governments, and to develop the structural digital twin. And we can develop further for the, we already have the parametric role, but we can do further for the extreme conditions and collision avoidance. So application and integrations is very promising. So this project was funded by DSME and also Korean governments. I appreciate it, and thank you for your attention. Okay, and this is the end.
Okay, my topic is safety regulation for decarbonization and digitalization. And then I would like to explain to you, actually, I'd like to share what is the current progress and current status of new rule development for decarbonization and digitalization. Yeah. So as I already explained, that I would like to share current progress of ERA rule guidance note for decarbonization and digitalization. Firstly, a decarbonization issue. Yet, as you know very well, that these are IMO has a clear greenhouse emission reduction target by 2050, net zero. 2023 IMO greenhouse gas strategy adopted at MEPC 80 and net zero greenhouse gas emission from international shipping by around 2050. And then we have a indicative checkpoint to reach this net zero greenhouse gas emission. For example, 20% reduction at least, striving 30% by 2030, and also 70% of reduction and striving for 80% by 2040 compared with 2008. As you know, these are regulatory drivers. Technical point of view, we have a design index, EEXI, and EEDI. And then operation point of view, we have a carbon intensity indicator, CII. A fuel point of view, life cycle emission standard, and also midterm greenhouse reduction measure. For example, fuel EU maritime and EU ETS and so on. This IMO regulatory landscape we prepared by CCC 9, based on CCC 9 last years. Currently, we have no mandatory instrument issued by IMO. However, we have interim guideline for various alternative fuel. For example, methanol and ethanol. Interim guidance is issued is 2020, and then fuel cell power installation 2022. And however, ammonia fuel interim guidance will be issued by IMO. Is expected to be end of 2024 this year. And then hydrogen fuel also expected to be approved by CCC during the CCC 10. And these are the summary of RR rule and guidance note for various alternative fuel. For example, requirement for ship using methanol as fuel, we already issued July 2021. Requirement for ship using ammonia as fuel, January 2023, and hydrogen case, March 2023, like this. Then let me explain in more detail about the methanol fuel. For gas carrier IBC base, no development up to date from IMO and RR. However, non-gas carrier IGF base interim guidance by IMO already issued December 2020. Based on this, RR rule requirement also issued October 2021, effective from 1 January 2022. Then ammonia fuel rule and regulation. As you know very well that IGC base, the use of cargo identified as a toxic product shall not be permitted. However, it needs to be amended in next MSC 109. And RR rule development work is on the way for ammonia fuel application to gas carrier by July this year. However, non-gas ship carrier IGF base interim guidance will be expected by MSC 109 at the end of this year. RR rule requirement using ammonia as fuel, we already issued the declarable rule in December 2020. Effective date is the 1st January 2023. Then hydrogen fuel rule and regulation for IGC base. For cargo, interim recommendation for carriage of liquid hydrogen in bulk 2016, but it needs to be updated. And then for fuel, no development up to date from IMO and RR. But for non-gas carrier IGF base, by IMO interim guidance will be expected and end of this year 2024. But RR rule we already issued it in March 2023 and effective date of 1st July 2023. This is a summary of RR future development and rule amendment plan for various alternative fuel. For example, rule for short carrier, January 2024, using ammonia cargo as fuel, July 2024 this year, and the hydrogen carrier, January 2025, and like this. And digitalization issue, current status of ERA rule and guidance note. In fact, if you look at the main business of classification society, safe regulation and inspection for ship design and operation is key. This day, when we see the new digitalization technology, new regulation and guidance are needed within the classification society. In the left box, mentioning various requirements for regulatory need. For example, cyber security measure, digital twin guidance for digital twin guidance, remote autonomous special design, AI-based digital solution, blockchain, and shoreside remote control and like this. So we are making great effort to exchange information with the various stakeholders, participating in the project, certify solution, and develop the standard regulation. And also we can see the increasingly strong requirement in new ship project due to the new digitalization trend. In the left paragraph mentioning the several new emerging requirements, something to be cyber secured, decarbonization related solution, CII, DCS, MRB, and remote access, operation, historical data collection and management, mobile enabled onboard network, and so on. However, there are still gaps in terms of regulation to satisfy these various requirements. In the right side of the paragraph, mass code is still being developed in IMO. Also, unfortunately, we don't have enough evidence for autonomous performance and new rule and regulation so far. Then Lloyd Register, we currently have 4 types of digital description: digital ship, digital compliance, digital health management, like a digital twin, and then digital compliance, cyber security, and unmanned marine system code. Currently, digital ship description is checking up with the capability of the monitoring and control by either remotely or autonomously, with or without crew on board the ship. And then the digital twin show the functionality of fault detection, diagnostic or prognostic. This may be used to identify and or trigger maintenance and or survey requirement and unmanned marine system code. Even small scale of vessel is dealing with the design framework. And this is our current situation of IMO developing new mass code, having some love plan when non-mandatory mass code is completed by second half of this year, and then mandatory mass code will be finalized by the end of 2028. Anyway, it may be a little bit late, but IMO current plan to create and apply the new mass regulation by 2028 is very important schedule that needs to be closely monitored. And then ERA issued the Maritime Trend 2050. The aim of this study was to explore the potential future for the maritime sector, and understand how this would manifest in the historical and specific scenario through the literature review, and then 16 in-depth quantified interview. This is, for example, this is the X is the speed of technology uptake, gradually or rapidly. And then vertical is the nature of global cooperation on the climate agenda. For example, just industry just adopt a new technology gradually, but cooperatively with the industry. It is the case, just the gradual transition. If that is the case, what if the nation embarrassed the widespread of adoption of green technology by 2050? And also industry adopt technology uptake rapidly, but globally collaboration way. It is the rapid tech-driven transition. If that is the case, what if automated technology solution become widely adopted in the maritime industry by 2050? Okay, next slide shows some change and good explanation about this one. Three case: new normal of a ship, and then knowledge assisted economy, and then customer clearance and ship repair in the metaverse. For example, new normal of a ship, remotely controlled and even fully autonomous commercial ship will be the new normal. In 2040, about 17% of global shipping fleet will be autonomous. And also knowledge assisted economy, reduction demand for seafarer by 22% in 2040. This will be offset by global trading increase anyway. And then human workforce will not be replaced by technology. Instead, knowledge economy. And then AI-based assistant tool, for example, chatbot. And then early use will be seen in service to assist the decarbonization impact. And then MR and ER, motion robot with AI-driven camera, and then hologram by connecting ship with a 3D virtual model like this. And then in the coming late 2020, essential innovation are expected in future ship design and operation, and the effective digital regulation development is being prepared for this. And then we at all will continue to work with the industry to develop the rule and regulation in time. Okay, thank you. That is all for now. Any question? Sorry, a little late.
No. It's not late at all. Yeah. Okay, thank you so much.